Hi guys, this is my first video on AS Maths and I'm going to be focusing on differentiation. Okay, so basically to differentiate is to get the gradient of a function or the gradient of a curve, or you can get a general expression that you use to find the gradient. But in simple terms, when we are differentiating, what we are interested in finding the gradient. Okay, so earlier on we've been introduced to the gradient as the change in y over change in x, which is delta y over delta x as per se. And what we used to do was to do the tangent of a given curve, and then we'll use the given tangent to calculate the gradient of the tangent. And when we have the gradient of the tangent, then we'll use it to find the gradient of the curve. All right, so I'm going to be using the first principles approach. First principles to find the gradient of a given curve. All right, let us consider the graph of the function y is equals to x squared. So I'm going to be having y is equals to f of x, which is equals to x squared. So f of x is actually going to be x squared. And I want to find the gradient at this point xy. Okay, so that is my point A, which is xy, and I actually want to find the gradient at that point A, which is xy. Okay, so from our previous knowledge, what we would do is to actually draw this on a graph paper, and then we do a tangent, and then we look for the gradient of the tangent. Okay, so suppose I'm going to be having the tangent here. Right, so the gradient of this tangent is definitely going to give me the gradient of the curve at the point A. But we know that drawing the graphs and everything on a graph paper is going to be very long and very tedious, and we won't have the time. So we'd rather have a calculative method, which we are going to be calling the first principles approach, that is going to help us to come up with the gradient of the curve. All right, so this point here is xy. Suppose I increase this point by a small increase that I'm going to be calling delta x, so that this point here, that is x plus delta x, this will automatically increase my value of y at this point to, I'll call this f of x plus delta x. So this is the increase in y. This is my increase in y, which is increase in y. And this is my increase in x, which is increase in x. Okay, so this is f of x. So this is the graph that we're having. And what we are saying is, if we want to find the tangent here, which is going to give us the gradient, we will have to reduce this line AB. We'll have to move this line AB to become the tangent. So I'll have to move this line to become the tangent there. So by so doing, what I'm actually doing, I am reducing this small increase in y from this point to back to x. Okay, so that the small increase becomes 0. So in other words, tangent means delta x is actually 0. So for me to get the tangent, it actually means delta x is 0, and when delta x is 0, I'll get the tangent, which is going to give me the gradient. So for me to find the gradient at point A, I'm going to be looking at the limit as delta x gets to 0 of the increase in y over increase in x of the line AB, which is going to be given by f of x plus delta x minus f of x, everything divided by delta x. So if I have the limit as delta x tends to 0 of the gradient of this, then I'll have the gradient of the tangent, which is going to be the gradient of the curve, and the gradient of the tangent is given by dy dx. This is pronounced dy dx, which means it's the gradient of the curve. So the gradient is going to be pronounced dy dx. So if I say find dy dx, then I'm actually going to be talking about finding the gradient of the curve. So the limit of this line AB as delta x tends to 0, which is going to be given by the limit of this expression here, should give me the gradient of the tangent, which is going to be the gradient of the curve. So let me put the actual value of f of x plus delta x. So f of x plus delta x is going to be x plus delta x squared minus f of x is going to be x squared, everything divided by delta x. So the limit of this as delta x tends to 0 should give me the gradient. I can actually calculate it. So limit as delta x tends to 0 of, if I expand this, I'm going to be having x squared plus delta x squared plus 2x delta x minus x squared everything over delta x. So what I've done is I've squared the last, squared the first, multiply everything else out, minus x squared as it was, everything divided by delta x. That should give me the gradient there. So I can simplify this. X and x can subtract each other, and I'll be left with this. And delta x squared plus 2x delta x, I can factor out the common thing, which is delta x. So I'm literally looking at the limit of delta x. That's going to be delta x, 2x plus delta x, everything over delta x. Okay. So that is going to be my dy dx. So dy dx, which is your gradient, is going to be, for this particular function, is going to be given by the limit as delta x gets to 0 of 2x plus delta x. And by saying limit as delta x tends to 0, if this is going to be insignificant enough, just as good as 0, that's what we are saying here by limit. So we're going to be saying this is going to be insignificant to be considered to be 0 is going to be 2x. So limit of delta x as delta x tends to 0 is going to be given by 2x, and this is our gradient function for delta x, or this is the grade. So this is our gradient function for f of x, which is actually our gradient in this case. So just to sum up what I've said from the top, in order to find the gradient at a, I considered a small increase so that I have delta y over delta x. Once I have delta y over delta x, I can find the increase of that, and that is going to give me the gradient function. And your gradient is going to be given by dy dx. So dy dx is going to be given by 2x in this case. Right, I'll give you more examples to help you understand how to find the gradient using the first principles, but basically this is the general approach of the first principles. Thank you.